Thanks very much, Mark. So I'm talking to you today about immutable or persistent data structures in Go. Now, I'm not even sure that's the right title, so if anyone has the correct title, please come and correct me at the end of this talk. So let me start by asking why use immutable or persistent data structures? Why are they useful? So this is based on my understanding of what that title actually means. So let's just take a look at a really simple example here where we've got a map, main function here where we create ourselves a map. We just print out the length of that map, and then we call to a function which will just print the elements in that map. Very, very basic here. And then we just confirm as well at the end that the map has the same length. So you can see, fairly simple setup here. So this is what I'm calling a good printer in this situation. The print function here is purely functional in what it's doing. So now I'm actually going to write a bad printer. And this bad printer does much the same thing, but it also modifies the map that I've passed in. Now, as the caller of this function, that might actually be clear to me if I read the documentation, and that sort of somewhat presupposes that the documentation was correct in the first place as well. But it also gets somewhat more complicated as well if printmap itself made a number of calls itself into other functions, other libraries, packages, etc. So documentation is good, and in this situation, it would have been good enough if we'd actually read it as the caller, and we would have therefore have expected the map to be effectively returned, if you like, or mutated as a result of the call. But in a number of situations, this isn't very good behavior. In fact, it's very poor behavior, particularly in a concurrent context. You absolutely don't want to do this if you want to make some sort of assurances about the values that you're passing into the functions, because they may be being referenced in a concurrent fashion. Okay, so this is what immutable/persistent data structures are all about, at least by my definition. So let's create ourselves one of these and create a better printer in this case. So I'm going to use GoGenerate, something I use a lot, and I've written a code generator called Immutable Gem, which helps with that. So in this situation, we're going to template ourselves a new type here, and the in_im_prefix is just a way of indicating to immutable gem. That's what we're doing. We're creating ourselves a new template type. So you can see here it's of the same type map string int as in the case we had before. Okay, that's great. So now let's run GoGenerate, and all that's going to do is actually create us another file here. And in this situation, you can see it's called gen_main_immutable gen. The details of that aren't particularly exciting. Okay. So now let's actually create this immutable printer. So before, you remember we just passed in a regular Go map. So things are slightly different now. And you'll see here we're also passing in our new type, but are specifically a pointer to that new type as well. Somewhat different semantics as well, not semantics, excuse me, syntax, excuse me, in terms of the ranging over that map that we've passed in, but it still looks pretty similar. We just have to call this .range on the map that we've passed in, but then you actually get a regular Go map out of that as well. And then at the end there, we're just calling m.set, because of course it's not a map anymore. It's actually, if you look under the covers, a struct type here. So it has a method defined on it called set. So where we're actually trying to modify the map, it's somewhat different. We're calling a method as opposed to using the index notation. Okay, so did this actually work? Well, here we've just got a very similar looking main function. And again, the initialization of the map is somewhat different, so you might be balking somewhat of the syntax at this point, but just go with it for a second. The length is derived in a slightly different way via a method as well. Then we're going to call the print map function that we declared on the previous slide, and then just check. Well, this looks pretty good because the length hasn't been modified in this situation. So how did this actually work? Well, points and prizes at the end of this presentation for someone can tell me what's slightly weird about this slide here. But this is actually sort of explaining what the interface, if I can call it that, is for the map that we've just defined here. You can see the length function, the length method there, which tells us what the length of the map is. But when we're actually calling set, and this is the critical one here, we're actually getting back effectively a copy of the map that was the receiver to the method call. So that means that the original map on which we called the .set method is actually totally unmodified, and instead the set applies to a copy of the original map. Now this is incredibly powerful because you can start to actually make fairly strong assurances in your code that if you have an immutable value of this type here, that you can just pass it around anywhere and know that you will always be looking at the same map, regardless of where else it's passed. And you can sort of start to imagine that that's an incredibly powerful construct, particularly in a concurrent situation. So this map, albeit via methods, implements all the same type of functionality that we have with a regular Go map. And indeed, the generator also supports immutable slices and struct types as well. They have their own sort of special interface, and I've just shown you the map one here. So all three of them actually share this fairly common immutable interface, as I'm calling it that. And again, points for people who can spot what's interesting about this slide. But this just this sort of explains that for any sort of immutable type value, that you have, you can call these methods. You can ask, is the thing that I have mutable? You can actually get a mutable copy of the original value. You can go the reverse direction as well. You can say, give me an immutable version of the mutable one that I might have. And with immutable are then just convenience functions for making your code a little more cleaned and easy to read. So if all this seems absolute garbage, let's just quickly go through for a quick recap here. Write immutable templates as regular Go types, and then using a nice little code generator to generate the actual concrete instances of those. And that all happens using Go generate with the immutable generator to explode those templates. That allows you to then write your code in terms of those generated immutable types. And then there's also a tool called Immutable Vet as well to make sure that your code remains safe and that you're not accessing effectively the internals of the generated types. I can say there's a tiny bit of further reading in the docs that exist, and I will post these slides on Twitter, but really that's just a bit more of an explanation, and there are plenty of motivating examples in the repo as well as the tests that sort of give you examples of how and why you might want to use these. But that's it for today. Thank you.